Do you know what is curing process in fiber-reinforced composite? It involves subjecting the composite to pressure and temperature cycles, preparing it for industrial applications. Numerical simulation of the curing process, however, is a challenging task. This video teaches you how to use Abaqus subroutines to simulate the curing process in composites. In the first section, we will provide an overview of the curing process in fiber-reinforced composites and discuss the thermo-chemo-mechanical simulation of this procedure. The second section begins by discussing the generation of strain components in FRCs during curing. Next, we will explore chemical shrinkage and thermo-expansion, which are two primary factors contributing to strain generation in composites and hold a significant influence on the final product. The third section explores a significant aspect of the thermo-chemo-mechanical simulation, the evaluation of stress components in the curing process of fiber-reinforced composites. In this section, we have examined several models proposed to predict stress in FRCs during the curing process. Following that, we have provided information on the specific models used in this lesson and explained why they were chosen. To analyze such a complex process, we need multiple Abaqus subroutines together. This is a topic covered in the fourth section of this lesson. It includes discussing the functions and roles of subroutines such as HETVAL, DISP, UEXPAN, USDFLD, and UMAT. Lastly, we will explore how these subroutines interact with each other to solve a problem. Now that you have understood the fundamental concepts in this package, we will discuss how the simulation process is conducted. By the end of the fifth section, you will understand how to use Abaqus subroutines for simulating the curing process. However, an essential part of learning remains simulation numerical examples. This includes writing subroutines and providing guidance or modeling procedures in Abaqus. To simplify this, we have included two workshops for you. Workshop 2 presents a detailed step-by-step analysis of a problem in Abaqus and teaches you how to write the required subroutines. Using a simple model named Chile alpha, in this workshop we will extract the residual stress in the laminate layers during the curing process. But you might wonder, how do you write subroutines for more complex yet accurate stress prediction models? This is covered in Workshop 3. Exploring the same problem addressed in Workshop 2, we will now utilize a more complex model called Chile T to calculate the stress. Upon exploring the workshops, you will acquire valuable insights into the thermo-chemo-mechanical analysis of the curing process in fiber-reinforced composites. Now let's present the lesson. The curing process is a crucial stage in producing fiber-reinforced composites. This process involves applying heat and pressure to the composite material. During the curing process, first the resin exhibits a viscose flow state. With the application of heat and temperature, the resin gradually gains stiffness while also experiences shrinkage. This indicates that the composite is in the curing process. Finally, the composite's elastic modulus stabilizes. To gain a clearer understanding, consider the changes in the resin stiffness during the curing process in the figure. Initially, the stiffness is quite low until the resin reaches the gel point. Afterward, it gradually increases until reaching the glass point. Finally, the composite achieves a fully cured stiffness and it is ready to be used in various industries. Now you should understand the importance of carefully conducting the curing process to create high-quality composites. Note that an incorrect curing process may result in excessive residual stresses within laminate layers. Hence, utilizing numerical models as cost-effective methods is a way to design a high-quality curing process for laminates, a topic we have covered in this lesson. However, two challenges arise. First, during curing, we have two heat sources, the applied temperature and the internal heat generated due to the chemical reactions. Analyzing heat distribution requires considering both effects, which is complex and necessitates advanced models. The second challenge is development of a numerical model that considers the effects of thermal expansions, chemical shrinkage, and the mechanical strains in the problem together. We will use the heat conduction and the Cure kinetics equation together to analyze the heat distribution in the composite. Moreover, we need to go further by including the mechanical aspects to develop a thermo-chemo-mechanical model. In the thermo-chemo-mechanical model, heat distribution depends on both the applied temperature and the internally generated heat. Moreover, the heat distribution and the chemical shrinkage contribute to introducing non-mechanical strains in the model. In such a model, non-mechanical strains rely on the curing level, applied temperature, and internally released heat. Additionally, two critical factors, including the degree of cure and temperature, affect the stress distribution. As a result, the mechanical fields rely on both the temperature distribution and the chemical reactions. Now that you have learned the basics, it is time to understand how to evaluate strain in composite during curing. Mechanical strains are calculated by Abaqus automatically, so no action is needed. The primary challenge lies in the evaluation of non-mechanical strains due to cure shrinkage and thermal expansion. In the context of fiber-reinforced composites, when the matrix material undergoes curing, it experiences a chemical reaction. This results in the release of gases, solvents, or other components. Then the release of substances can cause a decrease in volume within the composite, leading to what we refer to as chemical shrinkage. This phenomenon is very important for us as it causes the spring-forward effect. Here you can see a decrease in the enclosed angle of an L-shaped composite after curing, which is called the spring-forward phenomenon. The equation used to calculate cure shrinkage strains in composites indicates that a small change in the degree of cure generates strains in the composite. Here, alpha is the degree of cure and CCS, known as the effective chemical shrinkage coefficient, is another crucial factor. When we increase the temperature during curing, molecules within the material start vibrating and moving. This movement leads to the thermal expansion and dimensional changes in the composite. The difference between cure shrinkage and thermal expansion is that curing primarily occurs within the matrix. So, cure shrinkage relies solely on the resin's property. However, thermal strains depends on both the fiber and matrix properties because both contribute to the thermal expansions. The equation illustrates how temperature changes lead to the creation of thermal strains. Here, CTE stands for the effective thermal expansion coefficient. When discussing the calculation of stress in composites, you might think of Hooke's law. It calculates the stress, represented here by sigma, as a function of strain. Here, C represents the stiffness matrix. The equation sounds simple, but it is not that straightforward for composites during curing. Why, you ask? Look at the figure once more. As illustrated, the matrix stiffness and consequently the composite stiffness increase over time during curing. Hence, the stiffness matrix can change based on temperature, curing degree, or a combination of them. Generally, there are three recognized categories of models developed to predict residual stress in composites: linear elastic, viscoelastic, and path-dependent models. Since the models rely on the composite properties, we will focus on a well-known composite, Hercules AS4/35016 graphite exposite. However, after learning this lesson, you will be able to discover models for other types of composites and apply them to numerical simulations. Linear elastic models are the first and simplest formulations proposed to calculate stress in composites. Within this category, the Chile alpha is one of the most basic models. It describes the matrix modulus of elasticity as a function of the degree of cure, as shown in this equation. The Chile alpha model, though simple to use, has low accuracy. To enhance its precision, the model was later modified, giving rise to the Chile T model. Viscoelastic models are another category of stress prediction formulas in composites. In such models, stress depends on the relaxed stiffness matrix and two variables known as current and past reduced times. These models are more complex but offer greater accuracy compared to elastic models. Path-dependent models are another category of models simplifying the viscoelastic formulation. The presented models cover everything you need for the evaluation of stress in FRCs. For more details on this matter, you can explore the full learning package provided on our website. Note that in all of the suggested models, the stress depends on the temperature, the degree of cure, or a combination of them. So we require a thermo-chemical model to be used within the proposed stress prediction models. This forms the basic for the thermo-chemo-mechanical analysis in this lesson. For the thermo-chemical model, we have employed the heat conduction and cure kinetics equations. The model is used to study heat distribution within the material. Here, Q represents the internal heat source and its variation with respect to time is desired by this equation. Alpha stands for the degree of cure, and its variation with respect to time reflects the curing reaction rate. As you can see, the curing reaction rate depends on temperature and the degree of cure, and this function can vary between different materials. Here we are specifically using a function proposed for a AS4/3501-6 composites. We have used this model to evaluate temperature. Now let us look into the Abaqus subroutines required to apply the provided formulations. The first subroutine we need here is HETVAL. It is a useful tool that lets us specify the heat flux generated internally. We have used it to compute the heat flux during the curing process in this lesson. To use HETVAL in Abaqus when studying the composite properties, you must open the Edit Material window. Then click on the Thermal menu and choose Heat Generation. A step-by-step guide for writing the HETVAL subroutine for this lesson is available in the complete package provided on the CAE Assistant website. The second subroutine needed for simulating the curing process is DISP. It is used to define or modify boundary conditions, particularly to apply the cure temperature cycle. Another subroutine we need, UEXPAN, is designed to calculate incremental thermal strains in Abaqus. The UEXPAN subroutine is helpful for modeling complex scenarios where thermal strains are influenced by temperature or state variables. This feature does what we need for calculating the thermal expansion and shrinkage strains in composite during the curing process. To use the UEXPAN subroutine in Abaqus while setting material properties in the Edit Material window, go to the Mechanical menu and click Expansion. This action allows Abaqus to include the calculated non-mechanical strain values for each time step and location from the UEXPAN subroutine. In the provided learning package, we have given you a step-by-step guide on writing the EXPAN subroutine for simulating the curing process. The fourth subroutine required for this lesson is USDFLD. Many Abaqus subroutine users are already familiar with this subroutine as it has multiple general applications. It enables us to set field variables based on time or material point quantities. So we can use it to introduce material properties that depend on the solution. Its main function for us is updating state variables such as the degree of cure and cure rate and transferring them to other subroutines. To achieve USDFLD in the Abaqus model, when defining material properties in the Edit Material window, just choose the General menu and then click on User Defined Field. In the provided package, we have guided you step by step in writing the subroutine for the objectives of the lesson. The last subroutine we need is called UMAT. It is a tool that allows users to define the mechanical behavior of a material, particularly when the default Abaqus library models are not suitable. This subroutine enables the utilization of state variables to define material properties. Such a feature is essential for simulating the curing process. UMAT helps us in defining a model that describes the changes in the resin's modulus of elasticity during the curing process. To use UMAT in an Abaqus model, go to the General menu and choose User Material while defining material properties in the Edit Material window. Abaqus will now use the material's behavior as defined by the provided UMAT subroutine. This covers the basic information required for using the UMAT subroutine in this lesson. In the package, we will guide you step by step in writing the subroutine to define composite properties during the curing process. The first subroutine we have used is DISP, which solely depends on time and doesn't rely on other subroutines. It works independently in our work. But what about the other subroutines? They work together since they all rely on state variables. Based on the documentation, HETVAL is called after USDFLD, UMAT, and UEXPAN subroutines. Therefore, it utilizes the latest values of state variables from the other subroutines. UMAT is called before HETVAL, following USDFLD and UEXPAN. UEXPAN subroutine is called after USDFLD. According to the sequence of subroutine calls, USDFLD takes the initial action in our work. In USDFLD, we will update state variables such as the degree of cure and cure rate. The updated values will be utilized by subsequent subroutines. Cure rate information will then be set to UEXPAN, which computes cure shrinkage and thermal expansion increments. Subsequently, UMAT incorporates the degree of cure to calculate the Jacobian matrix and stress. Finally, HETVAL uses the cure rate and the degree of cure to determine the heat flux. In the provided workshop, we will offer detailed guidance on how to write these subroutines step by step. Now let us first summarize our objectives in this lesson. We have chosen a widely used composite known as AS4/3501-6 prepreg and will study its behavior in terms of thermal, chemical, and mechanical aspects. Our first goal, like what we have discussed in Lesson 1, is to study the internal heat generated during the curing process. To achieve this, we need to evaluate the degree of cure. Thereby, we have to analyze the curing process during the solution. This covers the thermo-chemical aspect of our simulation. Furthermore, we aim to compute the non-mechanical strains generated within the composite during the curing process. This is a new topic that was not covered in the first lesson. Later, we will examine the residual stress that arises in the composite throughout the curing process. This aspect corresponds with the thermo-chemo-mechanical analysis we are performing in this lesson. The stress calculation makes the end of our simulation process. Is simulating this process challenging for you? Don't worry. We know that the thermo-chemo-mechanical modeling of the curing process is a complex task. It necessitates a thorough understanding of the role of each subroutine and how to effectively manage them within problem. When you follow the provided learning package, you will see how easy it is to conduct the analysis with the presented step-by-step procedure. For verification processes, we have extracted the total temperature in a problem. The question is whether the model accurately predicts the stress within the laminate or not. We have also investigated this aspect. For verification, we utilized both the Chile alpha and Chile T models and extracted the stress versus time. As illustrated in the left side diagram, the obtained results closely match the reference solutions in the right side diagram. Therefore, both models have been accurately used in our analysis. However, you might be wondering why we have used two Chile models in this lesson. The answer lies in the diagram on the right side. While the Chile alpha model is simple, it diverges from the viscoelastic solution. Hence, we utilized it solely to write a basic UMAT subroutine for educational reasons. The Chile T model, unlike the simpler Chile alpha model, offers a greater accuracy but is considerably more complex. Now let's explore the workshops. In workshop 2, we will utilize the Chile alpha model to analyze the stress within fiber reinforced composites during the curing process. It is 10.16 centimeters in width and length and has a thickness of 2.54 centimeters. The fibers in the top and bottom layers align with the direction of the arrow, while those in the two middle layers are perpendicular to the top and bottom ones. In total, the composite has 4 layers. The material properties for the thermo-chemo-mechanical equations are presented in the full learning package. The other specification in this workshop involves defining the step in Abaqus. For the simulation, we implement a couple of temp displacement step in Abaqus. The boundary conditions for the problem are depicted in this figure. A pressure of 689 is applied to all faces of the composite except the top one during the curing process. The upper surface is fixed in the direction of the composite thickness, and the curing temperature cycle will be applied to all faces. Here is the presented curing temperature cycle that is to be applied. Note that we need to select elements compatible with coupled displacement temperature simulations. Therefore, we have chosen C3D8T elements. These are the key details to consider before we begin modeling and writing the subroutine. Now let's go through a step-by-step guide on how the simulation is performed in Abaqus. To start the simulation, we create an Abaqus standard explicit model. In this model, first we need to define the composites geometry. To reduce the computational costs, we have modeled only the analytical domain with symmetric boundary conditions applied appropriately. To start drawing, we click on the Create Part icon in the Part module. In the displayed window, we keep all the predefined options unchanged. However, we should adjust the approximate size to fit the sketch well within the drawing space. As we are using the SI system of units in this lesson, we have set the approximate size to 0.16 meters, ensuring it is approximately 3 times greater than the sketch's length. Click Continue to start drawing. To draw the composite, click on the Create Lines rectangle. The dimensions of the composite are 10.16 centimeters in both width and height, while we define them in meters. Draw a quarter of the composite and then cancel the procedure. Then click Done to save the drawing and define the extrusion depth. The extrusion depth is 2.54 centimeters, which we will convert to meters by dividing by 100, and then we will input it in the provided field. So we write 2.45 E minus 2 and click OK to close the window. The part will be generated. The composite is made up of 4 layers with the same thickness but varying fiber orientations. To accurately include the layers in the model, we divide the part into 4 partitions. Now let's define the composite properties. To do so, go to the Property module and start by creating the material. First, click on the Create Material icon. Specify the density by clicking on the General menu in the Edit Material window and then choose Density. The composite's density is 1,578 kilograms per cubic meter. Enter this value in the provided field. We also have 3 state variables within the subroutine codes, which need to be established in the material properties. To define them, go to the General menu and then click on DISP. Then specify the number of solution-dependent state variables, which in this case is equal to 3. Next, let's define the thermal properties. First, in the thermal menu, click on conductivity to define the thermal conductivity values in the X, Y, and Z directions. So Abaqus can calculate how heat spreads within the material. However, the conductivity varies in different directions within the composite, but it has only one field here. So we have to select orthotropic instead of isotropic from the type combo box in this window. Now input the conductivity coefficients in the fiber direction as K11 equal to 5.43. Then input the conductivity coefficients K22 and K33 both equal to 0.4135. After that, click again on the thermal menu and then choose the heat generation. Now Abaqus understands that it needs to extract heat flux information from the HETVAL subroutine. Another thing we have to do in this window is instruct Abaqus to calculate expansion using the UEXPAN subroutine. To do it, we click the mechanical menu, then choose expansion. Now set the combo box on orthotropic since the expansion coefficient differs from axis 1 to axis 2 or 3. To call the UEXPAN subroutine, we check the checkbox for Use User Subroutine UEXPAN. Now we have to confirm that we have used the USDFLD subroutine and therefore we need to activate the user-defined fields in Abaqus. To do this, in the Edit Material window, open the General menu and click on User-defined field. Finally, we need to specify that the material's mechanical behavior is defined in the UMAT subroutine. Click the General menu and choose User Material. As we have not used any mechanical constants, so we input 0 in the field to avoid leaving it empty. Now we have defined all the required properties. However, how can we ensure the USDFLD subroutine is called when there are no field variables in the model? It is easy. We have to use field variables in defining one of the material properties. For example, click again on the density and set the new number of field variables equal to 1. Note that there is only one field variable in the subroutine and it represents the degree of cure. Now we set the value of field 1 to negative 1000. So when field 1 is equal to negative 1000, the density is 1578. Press enter to open a new row. Now we set the density to 1578 and set the value of field 1 to positive 1000. So if field 1 is 1000, the density takes the same value of 1578. Based on this table for the values of the first field variable between negative 1000 and positive 1000, the density is a constant value. You know that the first field variable in the code is the degree of cure, which falls between 0 and 1, and so it is always within the defined range. Therefore, the density remains constant at 1578 in our simulations. Now we ensure that the USDFLD subroutine will be called by Abaqus since density depends on a field variable. Click OK to close the Edit Material window. We forgot to define the specific heat in the material properties. To define it, click on the Material Manager icon and then click Edit. Go to the Thermal menu, choose Specific Heat and then input its value equal to 862. Click OK to close the window. Now you must define a section and assign the material orientation. Next, we go to the Assembly module to create an instance of the model. Afterward, go to the Step module and create a new step. For the purposes of this workshop, we need to define a coupled temperature displacement step to consider both the thermal and mechanical fields. To create the step, click the Create Step icon. Choose Coupled Temp Displacement and click Continue. Let the response be transient and set the total time to 18,096. You can click OK to create the step. Now let's apply the load. To do it, first we go to the load module. The composite is first at room temperature and we will define such a condition using predefined fields. To do so, click on the Create Predefined Field tool from the toolbox area. Then ensure that Initial is chosen in the Step combo box. Choose Other for the category, then select Temperature Type for selected step and finally click Continue. Next, select the entire domain and click on Done. Now you need to define the room temperature in this window. Without altering the default settings for distribution in this window, set the room temperature equal to 298.15 Kelvin. This value is equal to 25 degrees Celsius. Click OK to save it. To apply the temperature cycle to the composite, click on the Create Boundary Condition tool. In the displayed window, select Step 1, click on Other and choose Temperature Type for the selected step. Click Continue and select the top, bottom, and 2 exterior sides of the composite. Finally, click on Done to confirm the selection. Now let us instruct Abaqus to retrieve the temperature history data from the DISP subroutine. To do so, choose User field from the Distribution combo box. Then enter a magnitude of 1, which will be multiplied by the values defined for U1 in the DISP subroutine. Finally, click OK to close the window. Now let's apply pressure to the composite. To apply pressure, click on the Create Load tool, choose Step 1 and select Mechanical category. Then click on Pressure and Continue. Select all faces except the top one and the symmetric planes. Then click Done. Input the magnitude as 689,000 in the display window and click OK. Now to make our simulation more realistic, let's constrain the displacement of the top face in the direction of the z-axis. To do so, click on Create Boundary Condition, choose the initial step, click on the Mechanical category and select Displacement Rotation. Click on Continue, select the top face and in the displayed window, check the U3 box, then click on OK. The last boundary condition to be defined is the symmetry condition, since we have modeled a quarter of the composite. To define the symmetry condition, click on Create Boundary Condition, choose the initial step, then click on the Mechanical category and finally select Symmetry, Anti-Symmetry, Incaster. Click Continue, choose the symmetry plane at the center of the composite, which is perpendicular to the y-axis, and then click on Done. In this window, click on the YSYMM radio button and click OK. Finally, repeat the process for the symmetry plane perpendicular to the x-axis. To do it, just click on the Create Boundary Condition tool, then make sure the initial step is chosen. Now click on the radio button for the Mechanical category. Select Symmetry, Anti-Symmetry, Incaster and then click on Continue. Now choose the symmetry plane at the center of the composite, which is perpendicular to the x-axis, and then click on Done. In this window, click on the X-Sim radio button and OK. This concludes the application of boundary conditions for the simulation of the curing process. Now you must start the meshing process. The modeling process is completed and now it is the time to submit the job to start the simulation. To do so, we go to the Job module and click on the Create Job icon. Then choose a name for your job and click Continue. To specify the location of the subroutine file, go to the General menu and click on Select to choose the Abaqus subroutine file. Once the Fortran file is selected, click OK. Finally, click OK again to close the Edit Job window. Now click the Job Manager icon and submit the job. Now it is time to check and verify the results. To start checking the results, we capture the composite's temperature at its center point. According to this figure, the results we obtained align well with the reference solution. This confirms the accuracy of our model. Let's explore another aspect of the composite's behavior during curing. In this figure, the red-colored line exactly matches the temperature boundary condition that we have applied. One point we have concluded from this figure is that when the applied temperature is constant, the temperature of the center point continues to increase. Afterward, it gradually stabilizes and reaches the applied temperature. This illustrates how the chemical reactions during curing contribute to the temperature increase at the center of the composite. It highlights the significance of considering these reactions in simulations and emphasizes the importance of writing the HETVAL subroutine in Abaqus as we have done. Now we have to check the degree of cure. As shown in this figure, the obtained result aligns with the reference solution, so the simulation model is accurate. Another crucial consideration in the curing process is analyzing the residual stresses within the laminate layers, as previously discussed. According to this figure, our obtained solution aligns with the reference paper, and thus our model accurately predicts stress within the laminate layers. Now it is time to explore the strain within the laminate layers during the curing process. The figure demonstrates that the model accurately predicted the total strain in the direction of the z-axis. Remember, we used the Chile alpha model in the second workshop just for simplicity. However, it had low accuracy in predicting the stress generated within the composite layers, as seen in the results. Workshop 3 is specifically designed to address this issue. To achieve this, we have used the Chile T model instead of the Chile alpha model to simulate the problem in the second workshop. This figure presents both the obtained result and the reference solution together. Note that the predicted curve is now more realistic compared to the previous workshop, thanks to using the Chile T model instead of the Chile alpha model. We hope this experience has been helpful for you and that you have gained valuable knowledge from this lesson that you can apply in your work. However, the main focus of this lesson, which is writing the subroutines, is a comprehensive aspect, and it is guided step by step in the provided package on our website. We suggest checking it and writing your comments. Have a nice day and goodbye.
Hello everybody and welcome to our new video training package of Abaqus, Curing Process Simulation in Abaqus. This package includes these sections. Lesson 1. Simulation of the curing process in fiber reinforced composites. Lesson 2. Thermo-chemo-mechanical simulation of curing process in fiber reinforced composites. Workshop 1. Simulation of the curing in a pre-preg laminate. Workshop 2. Thermo-chemo-mechanical analysis of the curing process. Workshop 3. Analysis of the curing process using the Chile T model. Thank you for taking the time to watch this video. We hope it will be useful for you.